We're going to be talking about parabolas again, in particular the locus definition of a parabola. So before we do that, let's kind of just review locus definitions that we've seen before. So for instance, we saw the locus definition of a line. So what is the locus definition of a line? Well, we have a couple of points, and then a line is the collection of all the points that are the same distance from both of those points. So I've got a point right in here that's the same different distance from both of those. And then imagine I have some kind of isosceles triangle, that vertex of that triangle up there. It's got to be the same distance from there as it is from there. And there's maybe a point out here, and a point here, even a point over here, the same distance from those. And in fact, if you take it, there's a whole bunch of points. And if you take all those points and collect them all together, you can see that it's going to make just a solid line. Okay, so that is the locus definition of a line, that it's the set of all points that are equidistant from two given points. We also had a locus definition for a circle. So in a circle, we're given a single point called the center. And then a circle is the collection or the set of all points that are the same distance from that one point. So we've got a point out here, it's that far away. We've got a point over here that's that far away. Well, there's another one here and another one here. There's a point over here that's that far away and here. And if we take and make a collection of all these points that are all the same distance away, of course we get a circle. So that is the locus definition for a circle. Okay, now these were useful to us because we actually used that idea to develop an equation for a line and an equation for a circle by picking an arbitrary point and calling it, x, y, and calculating this distance and this distance. They had to be equal. We set them equal, and then we were able to write the equation of the line. Similar for a circle. We just picked a random point and we knew that its distance had to be the same. We were able to use that to develop an equation for the circle. Well, the same is true for a parabola, which is what we're talking about today. So in a parabola, okay, so here we always have, notice we always have these sort of reference points. Here we've got a couple of points, 1 point. For a parabola we have one reference point called the focus, and we have a line called the directrix. Okay, and a parabola is the collection of all points that are the same distance from both the focus and the directrix. Okay, so imagine if I were to, look at this, right in between that would be one point. It's the same distance from the focus as it is from the directrix. Okay, and then if we were to choose another point, okay, maybe this point right here. It's this point from the focus, a straight line. And how do you find the distance from a point to a line? Well, you have to drop a perpendicular. Okay, so that distance and then the perpendicular down to this line would be the same. And so you can see that it would kind of go out like this. Okay, so the distance here is the same as dropping a perpendicular down there. The distance here, hopefully, this looks like it might be a little bit longer. I might not have drawn the perfect parabola, but that is the idea. It should be the same from here as it is to there. Okay, so that is the locus definition of a parabola. And just like with the line and with the circle, we can pick an arbitrary point on here and call it xy, and then use the fact that this distance is exactly the same as this distance to help us develop an equation for the parabola. Okay, and so in doing that, we're just going to first consider a simple parabola. I'm going to kind of redraw. I'm going to draw a parabola. Okay, and then maybe this is the focus, and let's say this is the directrix. So I'm just going to consider a parabola whose vertex is at the origin. So this is point 0, 0. That's the vertex. And so notice on this one I didn't label it, but this point that's halfway between that straight line distance, this is the vertex of the parabola. Okay. So this is the focus, and we're going to call this point 0P. Okay, so clearly it's got to be on that this line of symmetry about the y-axis, because that vertex is at 0, 0. And then we know that this is halfway between the focus and the directrix. This line is the directrix. So the point where it crosses here, well, this is P in the positive direction, so this has got to be P in the negative direction. So this is at negative P right here. Okay, so this is the line y equals negative P. Okay, and so what we're going to do is just choose some arbitrary point, xy, and when we look at, and this is obviously not a very good, well-drawn parabola, because if you look at the distance between here and my distance between here, believe it or not, those are the same. Okay, I should have had a much fatter parabola like that. So, sorry, we'll just use our imagination and pretend they're the same. Okay, so this distance and this distance are exactly the same. Okay. Now, because this parabola is centered at the origin, we know that it is equal to y equals some constant, let's just call that constant a, times x squared. So it's, you normally just think of a parabola being y equals x squared. That's the parent parabola. But, it could be wide like this, it could be narrow like this, I don't know. So there's some constant x squared. But we know that there's no, x minus h squared or y minus k, because it's not shifted. It's got a vertex at the origin. Okay. So that's the general form, but let's then figure out what exactly that a is and how is that constant related to the focus and directrix there. Okay, so we know, well, let's calculate this distance, d. Well, that distance, the distance between 2 points, is simply the square root of 0 minus x squared plus p minus y squared. Okay. And then the distance d, which is here, well, this is perpendicular. We know that this distance right here is p, and we know that this distance right here is y, because this is at point x, y, so this point is y, and this line is parallel to the x-axis, and it's p units away. So the total distance d there is y plus p. Okay. Now because these are the same, we can just set them equal to each other. So the square root of 0 minus x squared plus p minus y squared has to be the same as y plus p. Okay, so let's go ahead and square both sides. We'll square this side and square this side. So when we square this side, okay, 0 minus x is negative x, and when we square negative x, we'll get just x squared. Of course, we're taking the square root symbol away when we square it, so I'm just kind of in one step figuring out what that would be. And now we've got to square this, so we're going to get p squared, and then minus 2py plus y squared. And when we square this side, we're going to have y squared plus 2py plus p squared. Okay, so if we subtract p squared from both sides, those will go away. If we subtract y squared from both sides, those will go away. So let's put all of the y's on this side and leave the x squared over here. So we'll have x squared, and then we'll add 2py to this side, so we'll get rid of it, and we'll add the 2py to this side, and we'll end up with 4py. Alright, and then we'll divide, or let's multiply both sides by 1 over 4p. So this 4p cancels, and we're left with y is 1 over 4p times x squared. So we know the general equation is y equals ax squared. And here we've developed that y equals 1 over 4p times x squared. So that means this and this are the same. So we know that a has to be 1 over 4p. So that relationship right there is key. So if we know the equation of the parabola, then we just take that coefficient in front of the x squared term, and we can use that to say where the focus is and where the directrix is. Okay, so for example, let's just do a really quick example of this. Let's say we had, y equals 2x. So let's think about that parabola. Okay, so 1, 2, 3. Oh, sorry, 2x squared. 1, 2, 3. Okay, so when we put a 0 in there, we get 0. When we put 1 in there, we get 2. So it goes through that point. When we put 2 in there, we get 8. So 1, 2, 3, 4, 5, 6, 7. We're basically looking like that. Okay, so if we have the question, well, where is the focus and where are the directrix? Okay, well, we know that to find the focus and the directrix, that this 2 is really 1 over 4p times x squared. That's what it has to be. So this 2 has to be exactly the same as 1 over 4p, where p is the distance from the origin to the focus. Okay, so if 2 were equal to 1 over 4p, then we would have that 8p equals 1, and p is an eighth. So that means, okay, well, it's hard to put that point on here, but imagine there's a half, there's a quarter, there's an eighth, right in there is the focus, and then right here at an eighth is the directrix. They're very close together. And if we picked any point, the distance between this point right here, if I were to draw the straight line distance down there and the distance to the focus, they would be exactly the same. Okay, so once we know the equation of the parabola, we can easily find where the directrix and where the focus of that parabola are. You might also think about what if we had not this parabola but an upside down one. Let's say we have, y equals 1/3 x squared. Okay, so 0, 0 is the vertex. When we put 1 in, we get 1/3. Let's make this 1, 2, 3. That's 1, 2, 3. Okay, so at 1, we're going to be, sorry, I wanted it to be a negative 1/3. So if we put in a 1, we should get negative 1/3. So it's going to be right about there. If we put in 3, well, 3 squared is 9. So a third of that is going to be down at negative 3. So we're down here. And so our parabola looks like that. Not perfect. Needs a little more curve in there, but it's okay. All right, so again, where is our focus and where is our directrix? Well, just like before, we know that this number, negative 1/3, has to be 1/4p. Okay, so that means that negative 4p equals 3 if I kind of do a cross multiply, and p is negative 3/4. Okay, so p is down here at negative 3/4. So that's 0, negative 3/4. And then the directrix is at y equals positive 3/4. Okay, and then we should get that, you know, the distance here and the distance there are exactly the same. Okay, so with that in mind, we have some problems to do. So we want to find the coordinates of the focus and the equation for the directrix for the parabola y equals 2/7 x squared. Okay, so this is just like what we've done previously. We know that this right here, whatever coefficient is in front of the x squared term, that is related to the distance that the focus is from the origin. So we know that 2/7 is 1/4p. Okay, so if we do the cross multiply, we'll have 8p equals 7, and p is 7/8. So the focus is at 0, 7/8. And the directrix, well, that's got to be on the other side of the origin, so it's going to be at y equals negative 7/8. Okay. So once you know that relationship, that coefficient has to be 1/4p, finding the focus and directrix are very easy. All right. This is kind of going the other direction. This time we know what the focus and we know what that the vertex is at the origin, and we want to find the equation of the parabola. Okay, and we're going to sketch it. Let's go ahead and maybe start our sketch first. So the focus of the parabola is at 0, negative 5/3. Okay, so 0, let's say this is negative 5/3. Okay, so that is the focus. Okay, this is the vertex. It's at the origin. So we know that the distance here, this is p. And then at positive 5/3 up here, we know we're going to have the directrix. So you can kind of imagine what this parabola is going to look like. It's going to look like that, right? It might actually be a little bit wider, but that's kind of the general form. Okay, so how can I figure out what the equation is? Okay, well, we know that the coefficient, that this is going to be a y equals some number times x squared. Well, that a, we know, has to be 1/4p. Well, we know what p is. P is the distance from the focus to the vertex. Okay, and here's the tricky part. It's not just the absolute value, but if you actually want to get all the signs worked out correctly, you need to look at if it's down here at a -5/3, whatever the focus has at 0, -5/3. Okay, so that -5/3, that is P. It's a distance of 5/3 away, yes, but whatever the point is for the focus, that is the value you use for P. So if it's up here, you'll use a positive value. If it's down here, you'll use the negative value. So A is 1/4 times -5/3. Okay, so 4 times -5/3 is -20/3. And so A itself is -3/20. So the equation of this parabola would be y equals -3/20 x squared. And it makes sense that we have a negative value because it's a downward opening parabola. Okay. And the next one, we have a parabola that has a vertex of sorry, I needed to actually develop the formula for that one. On my last page I need some. Alright, that's all Weyl parabolas. We know that all the parabolas don't just always have their vertex at the origin. A lot of times they're shifted or translated in some direction. So imagine we've got this, if we have a parabola that looks like this, it's not right there. So it doesn't have that equation, just y equals some number times x squared. But it's close to that. Okay, so there is a line of symmetry here. There is a vertical translation here. Okay, and if it goes h in the, if this is at -h, and if this is at k, okay, then we'll have that y, minus k. So you subtract the translation for the y direction, and that will be, again, some number a times, and now we have to take into account, so that will be y, and this would be minus h or plus h, and you square that. So for this particular translated parabola, it would look like that. Okay. So in this particular instance, the vertex is at -hk. Okay, and then if we were to look at the focus and the directrix, so there's some up here somewhere is our focus, and somewhere down here is our directrix, and it will be p units in this direction and p units in this direction, and again this value right here is going to be 1/4p. Okay, so it's now, of course, we need to look then at what the coordinate would be, because it's kind of shifted as well. So the focus in this particular instance, okay, so it goes out to -h. That's that sort of line of symmetry. And then, okay, it's up k units, and then it's up another p units. So the focus will be at k plus p. And then the directrix is the line y equals, well, we start at the vertex, it's at height k, and we've got to come down p units to get to that. So it's at k minus p. Okay, so we should still be able to find all of the things that we need to. Okay, and then we have a line of symmetry. Here that goes right through the focus and the vertex as well at y equals negative h. Okay. So thinking about that, okay, we can solve this problem. We've got a parabola. It has a vertex negative 2, 1, like that. A focus of negative 2, negative 1, so its focus is actually down here. We might even go ahead and draw this. So we need to write the equation for the parabola itself, the directrix, and the axis of symmetry, and sketch the parabola. Let's kind of start with a sketch. I think that might be helpful. Okay, let's see here. So we've got a vertex of negative 2, 1. So negative 2, 1, that's the vertex. We've got a focus of negative 2, negative 1. So this is the focus. Okay, this is the vertex V, this is the focus. I'm going to just put F so we can keep track. Okay, so we need to figure out what the parabola is going to look like, what the equation for the parabola, then the directrix, the axis of symmetry, and sketch the parabola. Alright, so the easiest one is the axis of symmetry. Clearly, an axis of symmetry has to go through that vertex and the focus. That's going to be an axis of symmetry. So the axis of symmetry is going to be y equals, and whatever the x value of both the vertex and the focus are. So, sorry, not y, but x equals negative 2. Clearly it's the x value, not the y. Okay, so that takes care of the axis of symmetry. Okay, the directrix is probably the next easiest one. Okay, because we know that the distance between the focus and the vertex has to be exactly the same as the distance between the vertex and the directrix. Okay, so here, if this is length p, this also has to be length p, and your directrix has to be up here somewhere. Okay, so where is that at? Okay, this is 1, this is negative 1, so this distance is 2, so this distance also has to be 2. Okay, so this distance is 2, this distance also has to be 2. So that means the directrix is at y equals 3. Okay, so the last thing that we have to deal with now is the parabola itself. Okay, well, we know that it's shifted in the y direction up 1 unit, so we have a y minus 1 equals, we'll have to think about that in a minute, but let's do the shift for the x first. It shifted back 2, so that would be x minus negative 2. And now we have the little matter of the coefficient here. Okay, well, to figure out, well, we know what p is because we looked at the distance here. The distance of the value of p is 2. Okay, but in particular, should we have it as a positive 2 or a negative 2? Well, we need to look at where it is with respect to the vertex. So the vertex is here and the focus is down 2 units, not up 2 units. So it's actually a negative 2. Okay, so if you think about if we made this our new sort of our new origin, our translated origin, from that origin, it would be at 0, -2 if that were the origin. So the value has to be a -2. So we have 1 over 4p. P is -2. So we can stick that in there. All right. So now we should just be able to write this as y equals, so this is going to be -1/8 of x plus 2 squared, and I'll move the +1 over here. All right. And of course, if we had to draw this, it would go that way. All right. Now, one of the things that you might be asking yourself is, who would even care about this focus and directrix anyways? Why go through all this pain to find it? Well, there actually are a lot of applications of this, especially in physics, and there's one in your book. I'm not going to work through the problem, but I'm just going to look at this. And if you look at parabolic mirrors, and you want to find where all of the light rays will converge, that will be at the focus of the parabola that is the model for the shape of that parabolic reflector, the parabolic mirror. So we're talking about satellite dishes, things like that. So this is useful. It's not just some ridiculous thing that nobody would care about. So if you make a parabolic mirror, and they have a little example here, all right, well, they're making this mirror and they need to know where all the sound waves, light waves, whatever, this is a reflector, so this is light waves, where they're all going to be focused at. Where do you need to put that? At what distance from the bottom of the mirror here do you need to put that? Okay, and so this is an example. So they work through it. The equation for this parabola is 1/20th x squared. Where would the focus be? Well, that 1/20th, that is the 1 over 4p. So if 1/20th is 1 over 4p, that means p must be 5. So that means that focus has to be 5 feet, or whatever this was, feet, meters, whatever is away from there in order for this dish or this mirror to do its job correctly. So it isn't just a completely useless thing that nobody would care about. It actually would be used in reality. All right, so enjoy those problems.